Okay, so we've been talking about earthquakes. Some of this is going to be a review, and that's okay. So causes of earthquakes we talked about. You got plates moving against each other. These plates are really, they do move continuously, but the edges will catch, right? Pressure is going to build up, and eventually that spot where it's caught is going to break, and the plates sort of snap back so those parts that were caught catch up with the rest of that plate. Right? That rapid movement is what causes an earthquake. Right? And you can see that right in this section. Um, right? When we're talking about earthquakes, you're probably used to hearing the term epicenter. You probably have heard focus a little less often. Right? So a focus is actually that spot, like exactly where that movement happened. Right? And that's often well underground. Right? The epicenter is the spot on the surface that's directly above that focus. So epicenter is sort of, we can talk about that as a city, but it's always up at the surface. The focus is often deep underground. And that depth of the focus will affect how big the impact of that earthquake is. All right. Foreshocks and aftershocks are things you hear about on the news a lot. Right? Foreshocks, sometimes like as that pressure's starting to let go, there'll be some small earthquakes, right, that come before the major earthquake, and it can be, sometimes it's a few days leading up to it and lets you know something's happening. Sometimes, you might get a small foreshock, a small movement years ahead of time, right? It may not tell you anything. Aftershocks are ones that happen sort of as you had that pressure let go in that one spot after the major earthquake. The rest of the plate sort of, it changes the pressure and the rest of the plate's adjusting. So you get smaller aftershocks, right? Earthquakes that happen afterwards, and that may happen within often a few hours or days afterwards. Some of those are relatively minor. Some of those can be pretty big. So seismology is the study of those earthquake waves, right? And we've talked briefly in class about seismographs, right? And this is how the instrument that scientists use to detect earthquakes, right? And they can actually happen in a couple different ways. The simplest version is this pictured right here, and I'll post the pictures of this on as well. But basically, you've got a needle and a roll of paper that's moving continuously under the needle. So if the Earth's not moving at all, then it makes a nice straight line, right? But that needle is suspended, and so if the Earth starts moving, right, you're going to get squiggly lines on the paper, right? You oftentimes you're going to have one that's sort of detecting horizontal movement of Earth, and then one that's kind of a vertical thing that's going to detect if the Earth is moving up and down, because both of those things happen, right? And as you did your homework last night, you learned about the different types of waves. You know that P waves, those primary waves, are compression waves. Right? So that's like if we took a slinky and we pulled several of the coils together and let them go, we'd see that wave move along the slinky, and maybe that in class, maybe not. Those move really quickly. S waves are sort of the side-to-side waves, right? They can be up and down or side-to-side, but basically the direction of the wave is perpendicular to the direction in which it's traveling, right? So it's moving away from the epicenter, but it's moving side to side. Those move much slower. So in a seismograph, and as you can see right here, I'm going to try to zoom in. Okay. So as you can see in this seismograph down here, right, you can see the different waves as they hit the seismograph. So an earthquake happened, right? The P waves hit the location where the seismometer was. Right, you can see the P waves hit, they're smaller, right? They're compression waves, so they don't make it move as quickly. And then the S waves hit, and then you can see those kind of L waves, which are these slow ones that travel along the surface. Right? So if P and S waves, kind of like figuring out how far the process is somewhat like figuring out how far away a thunderstorm is, right? You're used to that. You count the seconds between when you see the flash and when you hear the thunder, because the speed of light is faster than the speed of sound. Right? Same thing. The speed of P waves is faster than the speed of S waves. So if you look at the time between when the P waves hit and when the S waves hit, you can use that difference to calculate how far away you are from the earthquake. And we're going to do that in class tomorrow. and you guys will figure out where is an earthquake, and then you'll do another similar exercise for homework. Right. And in order to figure out where the epicenter of an earthquake is, so if I'm standing in one place and I can looking at my seismograph and I say, okay, I'm 100 miles away, well, that tells me it could be anywhere within a radius of 100 miles. So in order to figure out exactly where the epicenter is, I need data from at least three different seismograph stations. Right, two of them I can kind of draw circles where they intersect, but I have probably two intersections, so I need a third one to figure out exactly where it is. It's the same way we triangulate locations with cell towers. Okay, so looking at earthquakes in the world, as we've talked about already, most of the earthquakes here, you can see each red dot is an earthquake, and they line up really well with the edges of plates. Right, here's the Great Rift Valley, you get the Mid-Atlantic Ridge, you've got the Ring of Fire, all of these different plate boundaries that you're familiar with. Right, earthquakes can vary in depth, and actually the triangulation to locate an earthquake really only works when it's a not deep earthquake, because those waves are traveling through the earth, so if it happens really deep, the distance is kind of not along the surface. But anything that's less than 70 kilometers we consider shallow. Right, 70 to 300 kilometers below the earth we consider an intermediate quake. Below 300 kilometers, it's a deep earthquake. Right, and how strong they are, we measure. There's actually a lot of different scales that are used. The Richter scale is the one that most people are most familiar with. Right, and as we've talked about in class, it measures how much shaking. So if you measure the height of those waves in the seismograph, right, that amplitude, and then it's the logarithmic scale of the log of the amplitude gives you the Richter scale. So as we talked about, each number has 10 times more shaking than the one before it. Right. Anything really over about a 4, you're going to feel. Right. You might feel a 3. So if you've felt earthquakes in New England, we're usually the ones that we feel are like in the 3 range. The earthquake in Japan that caused the tsunami was a 9.0, we think. Right, and what rank that is varies depending on who you talk to and what the measurements were. So the destruction that is caused by these earthquakes, and I apologize that I'm cutting off the view here a little bit, but we'll be okay. So different things can happen, right? You got the vibrations from the earthquake can cause buildings and bridges to collapse. You're probably pretty familiar with that. Buildings are designed to be earthquake resistant, which they often are. I know most of the ones in California have to be somewhat earthquake resistant. Same in Japan, right? Because earthquakes are common in those areas. So the buildings are designed in such a way that they can withstand that horizontal shear force. If that's the case, then a bigger earthquake is going to do less damage. In cases where the construction is not designed to withstand that, particularly in areas where the buildings are not in great shape to begin with, right? Smaller earthquakes can have much bigger damage, right? Haiti was the most deadly earthquake on record. It was a 7, in the 7 range. Not anywhere near a lot of the earthquakes. That would be kind of an everyday earthquake in Japan. But in Japan, it does a lot less damage because the buildings are earthquake resistant, whereas in Haiti, many buildings collapsed. Right? Another thing that can happen is liquefaction. Right? And I'll post a video of what this looks like. You could also just kind of do a Google video search. It's kind of cool. But liquefaction is basically, so if you've got soil that's saturated with water, right, which most soil is at a certain point underground, right, if you kind of shake that, because of the shaking, it actually becomes, instead of being a wet solid, becomes sort of like a liquid, right, kind of quicksand. And you can see that, there are good videos of it on YouTube, of that happening in real earthquakes. But one of the things can happen, so if you've got a building and it's above an area that then becomes, goes through liquefaction, you basically, now your building can collapse because it starts to sink, right? Or things that are underneath can float up to the surface, right? Like storage tanks or sewer lines. So if there's like a gas station has a buried tank, that can float up to the surface and cause all kinds of issues, right? We've talked about tsunamis. So basically what happens, there's 2 ways that you can have a tsunami, right? The one that we we're going to talk about most probably is when it's in subduction zone. So as we said, right here you've got your, right, this is your continental plate, there's your oceanic plate going underneath. Right, it catches, so it gets bent down, under. When it lets go, it pushes, it pops up, and that's going to push a wave of water up. That'll spread out, and then as it interacts with the shore and it gets near land, it becomes a very, very high wave. The other way that you can get it is if something falls into the water, right, which could be landslide or could be a meteor. In fact, the highest tsunami recorded on Earth that we know about was up in Alaska, where it was a landslide in a very narrow channel. The other thing that can happen is, well, a couple other things, is fire, right? One of them is fire. And this was a big issue. The San Francisco earthquake in the early 1900s basically decimated the entire city, and it wasn't, there was all kinds of damage caused by the earth shaking, but even worse was the fact that the entire city burned down afterwards. So earthquakes can cut gas lines and electric lines, and the combination of those two is bad, because electrical lines, if you've ever seen it when it's still live, it starts dancing around with lots of sparks, and if you have the gas pipes break, and now you've got gas leaking and electrical sparks, you get huge fires, right? And oftentimes you'll see any of the major earthquakes, there are fire issues, right? And at the same time, the water lines might be broken, so then your fire hydrants aren't going to work, right? And then the last thing is that earthquakes can also cause landslides, and in fact, the tsunami caused by the landslide in Alaska was actually originally caused by an earthquake, which then caused the cliff to let go and drop into the water. So those landslides can then cause sides of hills and cliffs and things to come down that destroys habitat and homes. All right, so this is it for today. Go back and review if anything you need to. Please do look up liquefaction on YouTube. You'll find something cool. Tomorrow we're going to get into locating an earthquake. So I will see you tomorrow.